Hi, dear students. Today we are discussing two more methods to find out the rate of a chemical reaction. So let us start with the first method, that is tirimetric method. Basically, in this method, a quenched aliquot is titrated against a standard solution to find out the concentration of a known compound like an acid or a base or iodine, etc. But before that, let us explain what do we mean by aliquot, what do you mean by quenching, and what do you mean by standard solution. Aliquot is a small portion of a reaction mixture, like 10 centimeter cube or 5 centimeter cube. So it is basically a small portion of a reaction mixture that is used for titration. It is taken in a conical flask. Quenching means the process in which the reaction between the reactant is stopped in aliquot by immersing the conical flask in ice bath or by adding some substance to stop the reaction. The very important thing to note that quenching is important to obtain accurate result because concentration does not change after quenching. And at the end, standard solution, it is a solution of known concentration. It is taken in burette. Well, let us discuss this process with the help of an example. Look at this reaction. In this reaction, you can see a compound propanone, an organic compound, is treated with iodine in the presence of acid as a catalyst. As a result, you will get different products. In this reaction, one of the reactant is iodine. So we can calculate the rate of this reaction by measuring decrease in the concentration of iodine divided by total time taken. Now, how would we measure the concentration of iodine at different time intervals? The concentration of iodine can be measured by iodometric titration because it involves iodine and thiosulfate. Basically, iodine is treated with sodium thiosulfate to convert them into iodide ions and other products. In this titration, we can find out the concentration of iodine with the help of a standard solution of sodium thiosulfate. The indicator used here is start solution and the endpoint will be blue, black to colorless. So for example, let us consider this reaction between propanone and iodine is taking place in a beaker. So that is a reaction mixture. In a burette, you have a standard solution of sodium thiosulfate, the concentration of which is known, for example, say 0.2 mole per decimeter cube. So fill the burette up to 0 centimeter cube with sodium thiosulfate, which is a standard solution. In a conical flask, transfer a small portion like 10 centimeter cube of reaction mixture that is called as aliquot to this conical flask and then start titration. We know that the concentration of iodine. Now start titration. But here, after transferring aliquot to the conical flask, we have to stop the reaction between propanone and iodine. Otherwise, the concentration of iodine will be not accurate. So we have to stop the reaction between propanone and iodine. For that, we can immerse this beaker in ice bath, or there is another method. You can use a quenching agent. For example, in this case, you know that what is the reaction? The reaction is between propanone and iodine. It requires acid as a catalyst. So without this acid, if you remove this acid, the reaction will stop. So if we add sodium carbonate or sodium bicarbonate to this solution, what will happen? It will remove this acid, because acid react with carbonates to form salt, water, and carbon dioxide. So we can remove acid from this reaction by adding a small amount of sodium carbonate or sodium bicarbonate. So as a result, the reaction between propanone and iodine will not take place further. So we can stop this reaction by adding sodium carbonate or sodium bicarbonate. Here, sodium carbonate or sodium bicarbonate is a quenching agent. So that is called as a quenching agent. So already we can add some quenching agent like sodium carbonate here in this specific case in a conical flask, then transfer aliquot to it and then start titration and find out the volume. But here, that is iodometric titration, we do not add start solution at the beginning as indicator. So start titration when the color of the aliquot, the reaction mixture becomes straw, then it is very close to the end point. That at that time just stop adding thiosulfate to it and add some starch solution to it. The starch solution will form a complex with iodine, with the remaining iodine and aliquot, and will form a blue-black complex. So the color will become blue-black. Again, start titration. When the color changes from blue-black to colorless, stop the reaction. That is the end point for this reaction. And find out the volume of thiosulfate used to react completely with iodine present in this aliquot. Then by using this formula, iodine and thiosulfate on right side, C1V1 over N1 is equal to C2V2 over N. By C1 we mean the concentration of iodine, which is not known, we have to calculate it. V1 is the volume of iodine used, that is actually the volume of aliquot, and 1 is the number of mole of iodine in a balanced equation, which is 1 mole here in this case. C2 means concentration of thiosulfate. It is standard one here. It is 0.2 mole per decimeter cube. V2 means volume of thiosulfate used. That is actually mean titer divided by N2. N2 here is the number of moles of sodium thiosulfate, which is 2 in this case. So putting all the values, rearranging this formula, you will get C1, which is the concentration of iodine. Now repeat this process in the same way after regular intervals of time, like at the beginning the concentration of iodine, say it is 1 mole per decimeter cube. After 30 seconds you are left with 0.8 mole, 60 seconds 0.6, 90 seconds 0.4 mole, then 120, then 150, then 180, and at 210 seconds all the iodine will be used up. So the concentration of iodine, because it is a reactant, is decreasing with the passage of time. You can draw a graph of concentration of iodine against time t in second, and you will get this type of graph. From this graph, you can calculate rate of the reaction. So here in this case, rate of the reaction will be del change in the concentration of iodine or decrease in the concentration of iodine divided by total time taken. So in this way, we'll be able to find out or to measure the rate of this reaction. The next method is measuring the rate of reaction by conductimetric method. The next method is rate of a reaction by conductimetric method. This method is used to measure the rate of those reactions which proceed with the change in number or size of ions. Number or size of ions. Basically, conductivity depends upon the concentration of ions and the size of ions. Smaller ions can conduct in a better way than larger ions because smaller ions can move faster. So that is the basic idea behind this method. For example, let us discuss this with the help of an example. Look at this example. This is a reaction between bromoethane and hydroxide ion in alkaline medium. So basically that is a nucleophilic substitution reaction in which bromide ions are replaced by hydroxide ions. There is no change in the number of ions, but the size of ions is going to change in this reaction. Hydroxide ions are smaller in size, bromide ions are larger in size. So with the passage of time, the conductivity of the reaction mixture will decrease because smaller ions are replaced by larger ions. So if we draw the graph of conductivity of the reaction mixture against time t, you will get this type of graph, and the rate will be equal to change in conductivity divided by total time taken. Look at this apparatus. This is a conductimeter which is used to measure the conductivity of a solution. These are two platinum electrode. This is a meter which will give you conductivity. So here we have a reaction mixture in this container. So at the beginning it will be having a specific conductivity due to the presence of hydroxide ions, but with the passage of time hydroxide ions will be replaced by bromide ions which are larger in size, which will move slower than hydroxide ions, so the conductivity will decrease.